Hello, welcome to Basics of Finite Element Analysis. This is the second part of this course. The first part was done a couple of months earlier, and today we are in the last week of this course. This is the third day of this particular week, and for the remaining portion of this week, we will essentially cover plane elasticity problem. And the reason we are covering this plane elasticity problem and trying to understand it in terms of its FEA formulation is because it involves two differential equations simultaneously, and in each differential equation we have two variables. So, and this is in two dimensions. So, it is a multi-dimensional problem with multiple variables, and once we get a good handle on this type of a problem, then we can understand this, we can extend our understanding to 3 dimensions relatively easily. So, we will discuss plane elasticity problem. So, consider a solid object such that it has uniform thickness. The thickness can be extremely small or it can be extremely large, but the thickness has to be uniform across the domain. So, and I have my axis. So, one axis is in the plane of the solid, other axis is in the z direction out of the plane, and the third axis is also in the plane of the solid. Okay. So, z is in the thickness direction and the other two directions are in the plane of the solid. So, the displacement in x direction is u, displacement in y direction is v, and as I said, the thickness of this solid is uniform across the entire surface. So, what I can say is that the solid is bounded by two parallel planes, z is equal to plus h over 2 and z is equal to minus h over 2. So, this origin is such that it is at the center of the solid, and the top surface is at a height h over 2 and the bottom surface is at a height minus h over 2. So, this height is how much? This is h. I can have some constraints on this solid. So, I can have a fixed right. I can also have a roller contact. I can also have again this thing fixed at a third point and so on and so forth. So, I have at some number of points I have fixed it. The other thing is that at any point on the edge of the domain, I have a normal, so it is normal to the edge, and this normal can have two components, one is nx and the other one is ny, and also I can have, let us say, along part of the edge I can have some force or external pressure, so I call it P0. So, what we want to understand is how does this solid behave when it is constrained at a finite number of locations and it is seeing forces on its boundary. Okay. So, there are two classes of problems. So, this is called a plane elasticity problem. It is elasticity problem because we are assuming that the material is elastic, it is elastic. So, as I keep on increasing my stress, I get a strain, and the relationship between stress and strain is a straight line, and if I remove the external force, the system comes back to its original position. That is the nature of elasticity, and we are assuming that it is linear elasticity because the curve is a straight line. It is plane elasticity because we do not worry about the third dimension. So, we are only worried about two dimensions. So, there are two types of elasticity problems, plane elasticity problems. The first one is plane stress problem. This is called a plane stress problem because the stresses only exist in the plane, they do not exist out of plane. If stress does not exist out of plane, then what stresses are 0 in this case? What are the different stresses? Sigma z is 0. Is there anything else? Shear stresses in xz and zy is 0. So, it is called a plane stress problem because the stresses out of plane, in the out of plane direction, they are 0. Now, this type of problem develops when h is very small compared to size of the solid. If the thickness, this h is extremely thin, if it is extremely thin, then we can make an approximation that sigma z and the shear stresses xz and zy, they will be pretty close to 0. They will not be exactly 0, but they will be fairly close, so we can make that approximation. So, this is one plane elasticity problem. The other plane elasticity problem is plane strain problem. And it is plane strain because the strains only exist in the plane. There are no out of plane strains. In plane stress problem, you can have out of plane strains. In plane strain problem, you can have out of plane stresses. So, here epsilon z is equal to 0, gamma yz is equal to 0, and gamma zx is equal to 0. And this happens when h is extremely large compared to the size of the problem. Okay, it is extremely large. So, if it is a very fat thing, the material provides sufficient restraint for motion to happen in the z direction, and if there is no strain happening in the z direction, then it is a plane strain problem. So, the thickness provides by itself, by virtue of its material, a significant amount of constraint, so that there is no strain in the z direction. So, we will analyze both these problems, but in a unified way, Okay. Now, we will not go into the mechanics of this problem, but such a plane elasticity problem is captured by an equation of motion, right. So, this equations of motion we get from Newton's laws. Okay. So, how many directions we are concerned with the motion of this object? 2. It can move in x direction, it can move in y direction. We are not bothered about the z direction motion because there are no forces acting in the z direction, and it is a plane elasticity problem. So, if motion can happen in x axis in the x direction and y direction, how many equations of motion we will have? 2 equations, one to govern the x direction motion, the other to govern y direction motion. So, first we will write down equations of motion, and this we essentially get from Newton's second law, force is equal to mass times acceleration. But if we do all the mathematics, this is the equation we get. So, here I am using sigma xy, which is same as tau xy, which is the shear stress. And then the second equation is okay. Here u is the displacement in x direction of what? Of any point in the, of any material point in the body, right. So, u changes with respect to x, y, and what else? Time. It can change with time also. If it is a steady state static problem, then the time is not important. But if it is a dynamic problem, then time is important. So, time is important. So, u is a function of x, y, and t. Similarly, v is a function of x, y, and t. And then fx, fy are body forces per unit volume, in x and y direction. What would be the example of fx? So, suppose this is the body, and suppose my x axis is like this, my y axis is like this, and z axis is in this normal direction. This is my x axis, this is my y axis, this is the z axis, and the body is oriented like this. There are no forces in the z direction, right. And the second thing is that the thickness of this is uniform. So, it is a plane elasticity problem. I can put some forces here, some force here, some force here, and I am constraining it like this. Okay. So, it is a plane elasticity problem. What would be the body force? Now, this body is also seeing gravity, it is seeing gravity, right. And what is the gravitational force? Density times volume times g, right. So, gravity is acting in this direction, but my x axis is like this, y axis is like this. So, there will be one component of gravity force in the x direction, another component in the y direction. So, those are body forces. So, these are the equations of motion. The second thing is we have strain stress relations. stress strain relations. So, what stresses we have in the system? Sigma x, sigma y, and I will actually call it sigma xy, and that equals zero, so it is, so these are the strains epsilon xx, epsilon yy and twice epsilon xy. So, a lot of times this shear strain, this is engendering shear strain, this equals twice of epsilon xy, which is, so this is engendering shear strain. And this is tensorial shear strain. Okay. So, here we are using tensorial shear strain, but I can replace this by gamma xy, it does not matter. So, this is the second set of equations. So, we have equation of motion, strain stress relations. The third equation are strain displacement relations. Okay, strain displacement relations. So, epsilon x is equal to del u over del x, epsilon y equals del v over del y, epsilon x y twice, which is same as engendering shear strain, this is equal to del u over del y plus del v over del x. And finally, so all these equations A, B, C are valid for both sets of problems, plane stress and plane strain problems. So, if we solve this set of equations, we can solve for both. If I use these equations, equations of motion, stress strain relations and strain displacement relations, we do not distinguish between plane stress and plane strain problem. The only difference comes in our definition of C11, C12, C21 and C66, because the values of these C's are different for plane stress and plane strain problem. So, what are these values? For plane stress problem, C11 equals E1 divided by 1 minus mu12 mu21. So, you may be wondering what is E1, mu12, mu21. Okay. So, what we are assuming is a material, and let us say this material has lot of fibers, and then all these fibers are bound together by some glue, by some matrix. So, if I, so this is direction 1, this is direction 2. So, if I pull it in one direction, it will have some modulus, right. For instance, wood, along the length of the fiber, wood is stiffer, so its E is higher. So, in the direction 1, its modulus is E1, in direction 2, its modulus is E2. These types of materials are called orthotropic materials. Orthotropic materials. And what we are also assuming is that one direction is same as x direction and two direction is same as y direction. Okay. So, C11 is this, C12 equals E2 divided by 1 minus mu21 mu12, C12 equals mu21 C11 minus mu12 C22, and C66 is equal to G12, which is the shear modulus. It is shear modulus. And for plane strain problem, these constants are different. C11 equals E1 minus 1 minus mu12 divided by 1 minus 2 mu12 mu21 minus mu12. C22 equals E2 into 1 minus mu12 mu21 divided by 1 plus mu12 1 minus mu12 minus 2 mu12 mu21, and C12 equals mu12 E2 by 1 minus mu12 minus 2 mu12 mu21, and C66 is equal to G12. So, these are the constants. So, if you have to solve a plane stress problem, you use these constants. If you have to solve plane strain problem, use these constants, but the solution procedure for solving the procedure for these equations is the same. And finally, if the material is isotropic, so here we have assumed that the material is orthotropic. If material is isotropic, for instance steel or regular materials, rubber, steel, not rubber, steel, aluminum, brass, bronze, things like that. In that case, for isotropic material, E1 is same as E2 is same as E. So, you can simplify these relations. Mu12 is equal to mu21 is equal to Poisson's ratio, and G12 is same as shear modulus, which is equal to E divided by 1 plus mu times 2. So, this is the overall plane elasticity problem definition. So, what we will do is we will close our discussion today here, and going forward we will now start developing the formulation for this problem and actually solve this problem over next couple of lectures, several lectures. Thank you and look forward to seeing you tomorrow. Bye.